Hi guys, my name is Mabalaya. This is the first example that we're going to do, and I chose this example 6.1 because I think it's quite important for your assignment that is posted on the My Unisa website. And I think I just want us to go through the example slowly, just to explain the concept, and hopefully this will help you understand how to approach composite beams where you have two different materials. It can actually be more than two materials that make up that beam. In this case, the example is made up of wood there and steel there. So let's get right onto the example and read what the problem as it's stated. Okay, so to start, a composite beam is constructed from wood and the steel reinforcing plate. The dimensions are given there and there, and the wood and steel are securely fastened to act as a single beam, and the beam is subjected to a positive bending moment of 6 kilonewton meters. Okay, so and we asked to calculate the largest tensile and compressive stresses in the wood material and the maximum and the minimum tensile stresses in the steel material. If the modulus of elasticity of material 1 is 10.5 gigapascals and the elastic modulus of the second material is 210 gigapascals. And the figure is shown here to help explain the problem. Okay, so there's our wood and there's our steel, and the material numbers are numbered accordingly. So there's material 1 and there's material 2. Okay, so so we now have to calculate the largest tensile and the largest compressive stresses. So now the question is, where do we start? Okay, so the first thing that we see that they're doing in this example is they're calculating the neutral axis. The question is, why would you start by calculating the neutral axis? Because the question is asking us to calculate the largest tensile and compressive stresses. Largest tensile and compressive stresses. So the question is, why would you start with the neutral axis? I think it's important to know that, okay, well, if we look at what we are being asked to calculate, which is maximum tensile and compressive stresses, if we were to actually go straight and try and attempt to calculate this from the equations that we have been given in equation 6.1, we know that if we have a composite beam, the applicable equation to use to calculate your maximum stresses is equation 6.7a and b. Okay, so you can just go back and recap there if you like. If we were to attempt to calculate the maximum stresses there, look at how the formula looks like, and this is quite similar even for compressive and tensile stresses. But just look at the variables in this formula. You've got H1 there. You've got, this is the moment which we've been given in the problem. You've got H1 there. What is H1? We know that H1 really is the distance of the local neutral axis of material 1 from the global neutral axis, which we've calculated, which is what we are calculating as the first one. Now remember that if we look at, just to explain what I mean when I say local neutral axis, if I could just quickly draw here, hope you can see. Okay. So let's say this is our problem. This is how it looks. And this is the steel part, and that's your wood. Now when I say the local, so this is the local neutral axis. If this part here of the wood is 150 long, when I say the local neutral axis, we know for sure that it's gonna be definitely here at the middle at 75, which is halfway. That's 75, and this is the local neutral axis. And for this one here, it's a local neutral axis for the steel part will be somewhere here in the middle. We know that the total length is 12 mils, so therefore this will be somewhere there 6 millimeters for sure. And the global neutral axis, will, however, will be somewhere here. We don't know, and we have to calculate that. That is what I mean when I say local and global neutral axis. Okay, now the point I'm making here is, if you look at this equation here, if you were to try and attempt this equation here, you'll see that you have to first know this h1 here, which is the distance from between the local neutral axis and the global neutral axis. You have to know that, and you also see that you also have to know the inertias, the moment of inertias of the two different materials. And this actually already gives you an approach that you need to follow. It tells you what you need to calculate first before you are able to calculate this. It tells you you have to calculate you locate the global neutral axis. In this case, it's just called the neutral axis. You don't have to call it the global neutral axis. And you also have to find the moments of inertia. That's precisely what they do, okay, in this example here. Okay, let's go back quickly to that question here. So the first thing is being calculated is the neutral axis, and we know that the correct formula to use is according to equation 6.4, and equation 6.4 is shown here. The integral of y dA is equals to ya. Essentially what this means is your ya here, the y1 rather, that is the distance between the two axes that I was talking about, the local neutral axis and the global neutral axis. And if you can have a look at this diagram here, I've drawn here the 75 millimeters here will give you the local neutral axis of wood, and that will be the axis. The distance between that axis and the global neutral axis, which is that one, is what we're looking for. That is my y. So essentially I'm saying is from that to that distance is y1, and we apply the similar concept when we calculate the first moment of the steel part. So as you can see here, we can see here that distance is h1 minus 75. So you can say h1, and you subtract 75, that will give you that distance which you're looking for. Okay, and you multiply that by a1. A1 is the area of material 1, and that's easy for us to calculate. It's basically length times breadth, that is 100 times 150 will give you the area of wood, that, and you leave it in that form. Okay, and then you do the same thing now for the steel part. You say y2 multiplied by a2. Now y2 must be the distance between the local neutral axis of the steel, which is that one there. I've drawn a black line there, I hope you can see somewhere there. And obviously this is in the middle of the 12 millimeters, so obviously the distance from there to there is 6 millimeters. And you'll notice also that in this expression here, we using h1 to determine that distance and not h2. We're doing that deliberately because you'll see later on that it just makes things easier for us to calculate h1. Once we know h1, we can easily find h2. Okay, so it's just to reduce the number of unknowns. So we'll have one unknown in our two equations. Okay, so that distance is essentially 156, which is 150 millimeters there, plus the 6 millimeters here, which will take you up until halfway, which is takes you up until the local neutral axis of the steel plate. And if you take that entire distance and you subtract h1, that should give you h2. Okay, that should give you h2. Sorry, y2, not h2, y2, which is the distance between that neutral axis, the global neutral axis, and this local neutral axis, yeah, y2. And you'll see there that is 156 subtract h1, and that should give you that distance. And I notice here there is, according to me, there is an error here. This, according to me, is supposed to actually be h1 minus 156. I've actually done the calculation to see how much difference does it cause at the final answer. It's not that big of a difference, and we'll get to that. So we've calculated these two things, and they explain here that A1 and A2 are the areas of parts 1 and parts 2. We know that. And Y1 and Y2 are the Y coordinates of the centroids of the respective areas. Okay, so I've been referring to it as the local neutral axis. I think this is a better term, easier one for you guys to remember. Just say the centroid of that area, the centroid of the wood, and the centroid of the steel plate. I think that's a simpler term. Mine is actually more complicated. Okay, so fine, let's refer to it as the centroids. Okay, and then from there on, you substitute the preceding expressions into equation 6.4, which gives the equation for locating the neutral axis as follows. So this is now an important expression or equation that we use to determine h1 and h2, and this is derived somewhere in your in chapter 6, and I won't get into the derivation here. I don't think you'll be required to know this, but please feel free to ask if you're required to do the derivation from our lecturer. I'll also do that. Please, let's engage on the discussion forum. Whatever questions you have, please, and any comments that you may have with regards to the video that I'm making here, please, let's engage, let's talk, and let's really help each other to learn the subject and enjoy it. Okay, so that's the expression that we're going to use to determine our h1 and h2. So essentially, we're just going to replace this integral here should be replaced by that expression there, and you'll see there that is h1 minus 75, subtract that h1 minus 75 multiplied by 1500, which is what we have there. And on this part here, the E1 and the E2 are already given. Is the modulus of elasticity, and then from this part here you also replace with that one. In my case, I will replace this with h1 minus 156. Okay, solving this equation, we obtain the distances h1 from the neutral axis to the top of the beam. Now this is quite important. I just wanted to show you quickly, there is quite an important point that you need to know when dealing with this problem. That is the units in this. If you note that, you'll notice that here is gigapascals that being used here, and there's millimeters and so forth. So, but what's really important to know is how to handle the units in this kind of a problem. So here's how we can actually simplify this problem. Please note that gigapascals. Put this like that. Okay. gigapascals is actually essentially as the same as megapascals times 10 to the 3. That's essentially what it means. And the reason I'm doing this is because here's where I'm going with this problem. MPa is the same thing as Newton per millimeter squared. Then you can still have your 10 to the 3 there, which is 1000. So sorry about that. Now you'll see the reason I want to leave it here in this form here is because we have a millimeter squared there, and this will be able to cancel out other terms in this expression here. If we go back to where we have replaced, yes, here, this one here. So it will have this here as Newton per millimeters. You'll see when you multiply when it multiplies with other terms, and when you divide and basically you solving for H1, your units will be able to balance out. So please, if this, because of this is millimeters, I changed the gigapascals to this here. The gigapascals will now be replaced by Newton per millimeter squared multiplied by 1000. And when you handle this problem, it end up, if I rewrite the same problem, this is actually equals to 10.5 times 10 to the 3, because this will give me Newton per millimeter squared. Okay, H1 minus 75, 1000, it's actually 15,000 millimeters squared, plus 210 times 10 to the 3, H1 minus 156, 1,200. This must be equals to 0. Okay, and there you go. And as you can see there, the number, the value of H1 is not that different from what is given. Essentially, it's pretty much the same. Yeah, even though it's quite strange because this is quite different though, the values that we've put down there. That is this one that I'm talking about in particular. So quickly, and then we found H1. Once we found H1, it's quite easy now to find H2, because we know that H1 and H2 will, in combined, H1 plus H2 are supposed to give me 150 plus 12, right? And this is, which is exactly what they do here. They're saying H2 is equals to 162 minus H1. Where does the 162 come from? The 162 comes from saying 150 plus 12 should give me that entire length is 162. If you take that and you subtract H1, you'll be left with H2. That's quite simple. Okay, and then that's it. You've basically located your neutral axis. And the second thing that you do, you calculate the moment of inertia. The moment of inertia of the the first area, that is area 1 and area 2. And remember why we're doing this. We're going to use the moments of inertia to calculate the maximum and the minimum stresses. Okay, so, and if you look at here, they're saying the moment of inertia is I1 and I2 of area A1 and A2 with respect to the neutral axis can be found by using the parallel axis theorem. See section 12.5 of chapter 12, beginning with area 1, figure 6.7. We get this. Just to refer you quickly to section 12.5. Section 12.5 says, if you look at this one here, I'm going to jump straight to the derivation or the answer that we're going to use. The equation essentially that's applicable to this is this one here. Essentially what this means is the moment of inertia of a particular, the moment of inertia essentially of this mass here is the local moment of inertia, or the moment of inertia about the local axis. Why am I saying that? You see, it's inertia about the xc. If you look at this diagram here, you see that you have your dA, and you're saying that moment of it, that mass there about this axis here, which is the local one, but we have a global one, and this is the big one. That's the global axis that we actually interested in. We're saying the moment of inertia of that mass or that element there about this long axis or the global axis is actually equals to that local one, the inertia about the local one, which is this one here, plus the area multiplied by the distance squared. What is that distance? Is d1. You'll see that distance 1 there. Distance 1 is d1, distance between that axis and that axis. Okay, please, and if you don't understand this question, the phenomenon of moment of inertia, I'll upload a link that will show you some YouTube videos that explain what moment of inertia is. Hopefully that will just clarify things, but I won't dwell into that now. I just wanted to show you the formula, just that you're familiar with this. This is what we'll be using now to determine the moment of inertia of the different areas of our problem, as we've shown there. Okay, so the first thing we do is that moment of inertia of the material 1. This is the moment of inertia about the local axis. Okay, the local axis is as I said, and we know that because our area is rectangular in shape, the formula is 1/12 ph3, base times height cubed. That is the moment of inertia. That's what it's equals to. Please go and have a look at your formula sheets or the moments of inertia for different shapes. It differs for a rod, it differs for as a rectangular shape as well. So please go and have a look at that. So this is the formula that we're using. You'll see here, so it's 1/12, and this is your base, and that is your height cubed. That is the local one, if you remember. So that is, if I could just, that is I xc plus a d1 squared. That is what it means. So I'm saying this entire part here is that one, and this entire part there is that one. Okay, so these are the moment of inertia about the neutral axis. Okay, so there we go. And we're saying 1/12, this is the local one, and there we go. The A is the area of that first area, which is wood, so it's 100 times 150, and D, that distance. Now distance between, the distance is h1 minus 75. Remember, A is the distance between the two axes, okay, or the centroid to the neutral axis. We know quite well that there is the centroid of wood and there's our neutral axis. That distance there, that distance essentially is h1, subtract that one, this will give you that distance, which is why you see here it's h1 minus 75 meters squared, and that gives us our initial one. And similarly for area 2, you do quite the same thing. I don't want to spend too much time here. Please, if you have any questions, ask and we can talk more about this on the website. Okay, and we continue to the second page of example 2, and basically it starts off by essentially checking whether the inertias that we've calculated previously make sense. And this is the way they do it. To check these calculations, we can determine the moment of inertia I of the entire cross-sectional area about the z-axis. So here's what they do. There is a formula here that's being used, is 1/3 times 100 times h3 plus 1/3 100 h2 cubed, and that should give you that, which agrees with that sum. Okay. Okay, so the first thing they do here is to calculate, to check that the calculations that we've done for the moment of inertias are correct, and this is shown here quite simply. It's 1/3 times 100. Okay, and here basically they start off by just checking that the moment of inertias that we calculated are correct. And please just recap on your chapter 6, the notes there, the physicist formulas is there on how to calculate the total moment of inertia of the entire cross-sectional area. This is just a check, okay? So please, and then now we proceed to calculating what we've actually been asked to calculate, which is the normal stresses in the material A1 and material 2, material 1, material 2. Okay, they calculated from the flexure formulas of the composite beams, and the equations are 67A, 67A and B. And the largest compressive stress in material A1 occurs at the top of the beam, where Y is equals to H1 is equals to 124 millimeters, and denoting the stress by sigma 1A, and using equation 67A, we get the following. And this formula, as I've said, is provided there. So we replace that moment. There's the positive moment here, and so with regards to the positive moment that's given there, how do we know where is bending and where is compression? So where is tension and where is it compression? If you look at this one here, they're saying that it's positive. It's a positive moment of 6 kilonewton, 6 kilonewton meters, and there is our cross section. So how do we know which side sees compression, which side sees tension? So if I were to use the right hand rule, so I shall do this. That is our Z. If I can just zoom out a little bit. If I were to use the positive, the right hand rule, I'd basically say this is my hand, and the thing, you notice that my thumb is pointing the Z axis there, and that is the the kind of bending that this cross section will be seeing. So you'll see that my fingers are going into the page, and therefore these forces here are going into the cross-sectional area at the very top there, and therefore that side will see compression, and that is this side here. This side here sees compression because of that. That's positive. It's positive. My thumb is facing the positive side of the z-axis. There we go, and that's essentially what it means. Okay, so there we know that this side here will see compression and that will see tension. All right, and now if you go back to this solution here, okay, we notice there that we notice that we get okay, so basically we notice that the stress, here's the formula that's given. We've got the moment is +1, and h1 is essentially the distance that I talked about. This from the centroid of that area 1 to the neutral axis is h1. These are the things that we've calculated with the first step. You replace there accordingly, and this side here you replace with E1. It is a modulus of elasticity, and the units here are also very important. I'm going to deal with that quite shortly, just now. And you'll see here there's E1 as well. It's given, and then the moment of inertia of the first area, which is area 1, and then you replace here accordingly as well. That's E1, and therefore I1, which you've calculated. Notice here the answer is megapascals. Okay, because it's in megapascals. Please be careful of your units. The way you should handle these units is as follows. Okay, essentially this is, that is the same thing as 6 kilonewtons. You should take 6 multiplied by 10 to the 3. That will give you Newton meters, which is what you learned. Okay, and I'm now putting everything as a Newton and meters, and not Newton millimeters. Okay, you could do that as well, but it just depends on how you want to do it. It's just make sure that you understand what you're doing. And the way I'm going to show you now is where we use all our units as newtons and meters and not millimeters. Okay, and this is multiplied by 124.8. It's millimeters. I'm going to change it to meters by dividing it by 1,000. This is the same thing as dividing it by 1,000, and I can put a meters there, and multiplied by 10.5. 10.5 gigapascals is the same thing as 10.5 times 10 to the 9 gigapascals, which is Newton per meter. Newton per meter is Pascal. Sorry about that. And if we go to the numerator, we do exactly the same. So we're going to have 10.5 times 10 to the 9 Newton per meter. Sorry, that's Newton per meter squared. What did I say? Newton per meter squared. Okay, and this is multiplied by 65.33 times 10 to the 6. Now we have millimeters cubed. So perhaps we can change this millimeters to the exponent of 4 to meters to the exponent of 4. It's really it's getting quite tedious. but it's fine. Let's do that. The way I go about doing that is, for me to know how much do I divide by or multiply by, I usually follow this method here. I say, well, we have millimeter to the exponent of 4, and I want to change this to meters. Okay, so I'll just basically say, well, a millimeter, and I want to change this to become a meter. Okay, I want to change this to become a meter. So what do? I know that 1,000 millimeters will give me a meter. Okay, so essentially 1,000 millimeters will give me a meter. So if I put 1,000 millimeters here, it should give me a meter, right? So therefore 1 millimeter is equals to 1 meter divided by 1,000. Is that all right? Are you okay with that? Okay, so therefore obviously if I put this to the power 4, I should put everything here to the power 4 as well. So therefore millimeter to the exponent of 4 is equals to meters to the exponent of 4 divided by 1,000 to the exponent of 4, which is essentially 1,000 to the exponent of 4, which is the same thing as meters to the exponent of 4 times 10 to the exponent of minus 12. That's essentially what this means, that 1 millimeter to the exponent of 4 is the same thing as 10 to the minus 12 meters to the exponent of 4. I hope that makes sense. So I'm going to replace all my millimeters to the exponent of 4 accordingly in this expression here. We were still here. Okay, with 10 to the exponent of 6, and then here I can just multiply this part by 10 to the exponent of minus 12, and this is plus 210 to the exponent of 9 8.4229 times 10 to the 6 Newton per meter squared. And if you'd like to check if the Newton, the units cancel out properly, you can just do that as your own exercise. Otherwise this will take too long. Okay, that's essentially what they do to calculate the normal stresses here, which is the maximum, which is the compressive stress on material 1, and they do the same thing for material 1 again, but now for compressive. So that's for tensile. That's negative shows that is compressive, and positive shows that it's negative. It's a tensile, and you apply the same principle really to do the tensile and the compressive stresses for the steel. So please, okay, so please, that's that. Please let's talk more on the my UNISA website about this example. If there's anything that you don't understand or I didn't explain properly, this is my first video, so please excuse me. I'll do more videos, and hopefully I'll get better with time, and I can be able to explain and help you understand this better. So please, I may have made some certain assumptions that you understand certain things. Please excuse me. I would apologize, but please don't let it slide that easily mentioned on the forums, I'll be more than willing to help you and assist you. You're probably not the only person that has that issue. Please mention it, raise it on the discussion forum that I've left out an important point that you would like further explanation on, and I'll do exactly that, and I'll explain it to you without any problems. So thank you, and I hope this helps. I'll do the example 2 in the next couple of days. Thank you.